implications of unprojection. So I'll give a reminder of what that is, and then I'll talk about some constructions of surfaces. So this is sort of basically all work of around the work of Horikawa, but of course my approach is much more algebraic. And then the second part is sort of, and these are, you know, here you start off saying you want to do something with surfaces of general type, and a priori there isn't any restriction on you know, what ring you're working with, but it turns out that that there are lots of interesting questions here that come down to codimension 4. So here, this is the first lecture. The second lecture is really about much higher codimension. So I'll talk about some examples, including some of the results of the thesis of Sohail Iqbal, which was submitted last week, and that's partly supported by the WCU project. So let me remind you about this. I have X in some weighted projective space. Let me write WP there just to remind you, and I'm not going to write A1 up to AN, right? And then I have some divisor D. So I'm assuming that this guy is projectively Gorenstein. So projectively Gorenstein means that the homogeneous coordinate ring of X, which is the homogeneous coordinate ring of the weighted projective space, let's say X naught up to Xn. I call this N, and these are X naught up to Xn coordinates. So as I said, these are weighted divided by Ix. I want this to be a Gorenstein graded ring. And that means it has in particular an integer associated with Kx. So the omega x is Ox of Kx. So for a local ring, Gorenstein means that the dualizing sheaf is the trivial sheaf. For a graded ring, it means that the homogeneous coordinate dualizing sheaf is, it's the trivial sheaf. It's the Serre twist of a trivial sheaf. So this is this guy here is the sheaf of modules that corresponds to the free module of rank 1. Right. So I'm assuming also that D is projectively Gorenstein, and this is codimension 1. So later on, of course, I'll expect X to be sort of fairly non-singular and D to be a divisor, a Cartier divisor or a Q-Cartier divisor in it. But that's not necessary here. Here I need X. X could be completely reduced, or D could be completely contained in the singular locus of X as far as this algebraic. Also, so there's also the assumption that D is also projectively Gorenstein, and then there's this assumption that Kx is greater than Kd. So the same thing there. So then there exists a y in P. So this is n plus 1. So this would have weights with a new variable S. weight kx minus kd. Right, and then there's this unprojection map here. And so the point is we're just adding a single new variable, and this variable s is essentially the generator of, so let me write it in inverted commas. This is true if I have some kind of non-singularity and some kind of divisor. So this is something whose residue maps to omega d. Okay, so the algebraic assumptions I have say that I can find an element in here. So formally speaking, as I explained a while back, this is Hom of the ideal of d into omega x, which, when I take the Poincare residue of it to d, gives me the local generator. And there's a little twist here of degrees that I'm not explaining properly. Right, and y is again projectively current stuff. So, you know, I mean, the case to think about is L in S3 in P4, in P3. Right, so this is a line in a cubic surface contained in P3. Then I can find another surface here, which is T4, which is mapping down to it there, where this is now a point. So this is a line on a cubic surface. It's a -1 curve, and the map the other way back, the map the other way is just the contraction of that line to a point, and the T4 is intersection of two quadrates. So, you know, this is to remind, this is mnemonic. This helps you remember. Here I have Ks is -1 and Kl is -2. Right? And so when I add one new variable, I have to add one new variable of degree 1, and there he is. Okay, so let me give applications. So I have this paper called Graded Rings and Birational Geometry, around 2000. It's on my website. So this gives lots of these examples. So I'm not, so if you're interested in this material, then I'm not saying all of the things. So there are several examples here where you can construct new varieties using these methods. So here I want to talk about this, these two cases of Horikawa. So Horikawa studies, this is Horikawa's first sort of big paper in this subject, PG equals 4, K squared equals 5. And then there's another paper which is PG equals 3, K squared equals 4. Right? And the issue is we want to construct every surface with these invariants. So here you can make your surface by taking x5 in P3. However, it's not true that every surface with these invariants is like this. Let me assume K is ample. I mean, there are sort of other issues here, but I just don't want to get into them. So, and X is non-singular. So I'm ignoring the question of Duval singularities. So this is one possible model, and there's another model. There's a type family 2. Family 2, which have the property that when I try to map X to projective space, there's a base point, and the map is 2 to 1 to a quadric surface in P3. Right? So the phi kx blows up a point about, so a base point P, the base point of the canonical class, and then maps 2 to 1. Right, so, if you have to prove that this exists, you start saying what the quadric is, and you start saying what the branch divisor is, and you do techniques that everybody who studies algebraic surface knows very well. And my issue is not constructing this guy and constructing this guy, but constructing them together in a family. Right? And then there's a sort of basically similar thing here. You can make X as X for in weighted projective space 1, 1, 1, 2, 2. But it's also possible that Kx has 1 or 2 base points. And then you get models of X, not in this space, but in some bigger space, bigger codimension. And one of these, the case where there are 2 base points, is this, I'll get codimension 4. And these are quite delicate calculations, and to tell the truth, they're still sort of motivating my study of these codimension 4 things. So I had a student called Duncan Dix, around 1985, Warwick, PhD. And I think there are still sort of unsolved problems. In other words, in this case, I get a codimension 4 ring, and I don't yet know everything about that ring. I know enough to get back Horikowa's results. So I'm going to talk around this, and I'm not going to finish it completely satisfactorily, and that's sort of because the subject itself is not completely finished. Anyway, this is here. There's a really very, very elegant solution to all the problems. We understand everything. So let me say this very briefly. I'm mainly saying this as a prelude to this. I think I lectured on this here a bit before on this a few weeks ago. Right. So what I'm going to do is say here, let me take C, a curve in X. So X is a surface, obviously surface of general type, because Kx is ample. Right. So I'm taking. Let me just assume it have a non-singular curve. And then I'm also assuming that Kx has a base point. And so when I do Kx restricted to C, there's a surjective map of cohomology groups and of cohomology here. And so this thing here is a linear system. So the only possibility is that P plus twice a G12 on a hyperelliptic curve. Yeah? So I've got a non-singular curve here. I've got a linear system on the surface. I restrict the linear system from the surface down to the curve. I get a linear system which has got degree 5 and dimension 4. And it's got a base point. And so the only possibility by Clifford's theorem is that it's twice a G12. So the picture is that here is my curve C. It's a 2-to-1 map to P1, and one of these points is sort of singled out as the point P. Yeah? And so that's if I take the curve C is contained in X, it's really a hyperplane section of this picture, and then the curve C is getting mapped to a conic in P2, and there's a fixed point here, which is this one. This must be necessarily a Weierstrass point, necessarily one of the branch points of the cover. Okay. So the curve C itself is a sort of explicit object. We can calculate, of course, calculate the genus of C. So the genus of C is K squared plus 1, 6. And so it has 2G plus 2 is 14 base points. And I've separated them out as P, which is really sort of P naught, and then plus P1 plus P13. Right. And so in this context, if I choose coordinates T1, T2 in the plane, on P1, so I want to understand this graded ring, and you know, you should sort of think about this carefully. I want the way to see it is to see it as a subring of a bigger ring. So there's a bigger ring, including OC included into OC of P. Right, this is U. Right, so a completely trivial operation. I'm saying this is the sheaf of functions with poles on, with allowed a pole on P, and this is just the inclusion of the ordinary structure sheaf into this divisorial sheaf. Right, and then T1, T2, and these are sections of OC of 2P, and I can assume that T1 is U squared, and then T2 is the other coordinate. Right, so I'm assuming that this is the point where U is 0. Right, and so, you know, this is a bigger ring. So in this game, if you can put your stuff in a bigger ring, the bigger ring is always much easier to understand. Well, it's frequently easier to understand. Right? And so I need one other thing here, which is I need this inclusion V. So this was the inclusion of OC into OC of P. So there's also an inclusion of OC into OC of P1 plus P13. So, you know, these guys here, U, T1, T2, and V, are sort of generators of some bigger ring. And the ring that we want is the ring of, the thing I want is the ring of P of C and 2G1 plus P. And that's this is contained in the ring of U, T1, T2, V. Right?
In your picture, P is one of the 14 Weierstrass points upstairs, right?
Yeah.
Despite the label.
Yes. Yes. Thank you.
So that's why you write T1 equals U squared.
Yeah. Yes. So T1 is the point. You know, I mean, if you want me to call this one Q, by all means. So there are 14 branch points in P1 that I call P and P1 up to P13, and there are 14 Weierstrass points on the curve that I call by the same letters. Yeah. And so, you know, here I have a very simple structure. I have U squared equals T1, and I have V squared equals F13 of T1, T2. And I'm not sort of giving this a ring, and this is, you know, if you want a kind of Cox ring or something, a multi-graded ring, I'm not really concerned very much with this. The thing I'm concerned with is what this one is. So in degree 1, the thing I've got in degree 1, so it's this, P plus 2G12. So how can I cook up from here divisors that are sections, so sections of this sheaf? And the way is to do U T1 squared, U T1 T2, U T2 squared. Right, so the U's basically playing no part at all here. What's happening here is T1 squared, T1 T2, T2 squared is twice the G12, and it's mapping the curve here, C, to a plane conic, and that's all. However, writing the U here means I take account of the fact that these guys, the linear system has a base point, and therefore they're elements in this half-canonical divisor. Right, so in degree 2, well, the linear system I've got is now 5 times the G12, so this is also the canonical class of C, and so there are going to be 6 elements in there, and so, you know, I call these x1, x2, and x3, and the thing I'm going to get is x1 squared, x1, x2, x1, x3, which is the same thing as x2 squared, and then x1, x2, x3, x3 squared, right? And then I need a new element, which I'm going to call him y. Yeah? So I mean, I hope this is clear. These are elements in this ring. If I take monomials in them, I take products of them, then they're elements of this vector space, right, in degree 2. And as you can see, I'm going to get the relations here, x1, x2, x2, x3, x3 squared, and y. Right, so this element, these elements can of course be written as this one x1 squared is t1 to the 5th, this one x1, x2 is t1 to the 4th, t2, and so on. Right, and then the y is t2 to the 5th. Right, so I'm seeing already wedge 2 of this guy equals 0. Right, so because that's just because, you know, this x3 squared again, for example, is t1, t2 to the 4th. It's the square of this, and u squared is t1. Okay, so what do we get in degree 3? So, you know, the thing you need to know is that the sum of the Weierstrass points are in 2g plus 2. Are in g plus 1 times the g12. So if you take that into account, the thing you have to write down here is v times t1 and v times t2. Yes? So let me just say, v here has 13 zeros. Right? So I have v and t1, that has degree 15. This is a section of some sheaf of degree 15. Right? And it so happens that these guys here are in 7g12 plus p. So this is the same thing as that's right. So this one has this point here to the power of 15 and those points, and then the other one moves away. So these are the guys that are and monomials in x1, x3, y of degree 3. Right? So when I do this, I call these ones Z1 and Z2. Right? And just because they're formed from VT1 and VT2, the ratio between them is the same as the ratio between these. right? And so I'm getting these, you can see we started off with a very simple ring, namely just a hypersurface, and you might think, well, you know, the way a hypersurface is going to degenerate is going to be some, you know, to some maybe codimension 2 or codimension 3, but that's not what's happening. What's happening is we need, just because we have this base point, I need to put in one element here to get back the function which is not 0 at the point, and then I need to put in both of these guys here in degree 3, because I don't yet have anything in degree 3. So this is going to be codimension 4. And, you know, these relations, so, and then the equation v squared equals f13 of t1, t2 gives 3 new equations. z1 squared, z1, z2, z2 squared. Yes?
Sorry, I'm being a bit slow. So VT1, for instance, that's just giving the sum of all 14 bitrans points plus an extra p. That's why it's in the right limit.
Yes, that's right. So, you know, the sum of the Weierstrass points is linearly equivalent to whatever it is. There are 2g plus 2 of them, so it's g plus 1 times the g12. Yeah? Or you could also... So what am I going to write here? What am I going to write here on the right-hand side? So, you know, if you think about this, because this is a hyperelliptic curve, because the curve C is a hyperelliptic curve, if I take the linear systems I'm talking about and push them down to P1, they break up into an invariant and an anti-invariant piece. So these Z1 and Z2, so the U and V I want to think of as being symmetric under the hyperelliptic involution, and the V I want to think of being anti-symmetric. And so these guys here are anti-symmetric, so when I take their square, they're going to be, so, you know, the Z1 squared is really T1 squared times F13. Right? However, you know, this is in terms of all of these ring elements, right? And they're not in the ring that I'm allowed to say. Right? They're not in the ring I'm trying to describe. Right? So what I'm going to do is I'm going to take this thing and say, well, it's a polynomial of degree 15 in these variables x. It's a polynomial of degree 15 in t1 squared, t1, t2, t2. It's a polynomial of degree 15 in t1 and t2, and then I'm going to write it as a polynomial of degree 3 in x1, x2, and y. Sorry, of degree 6 in x1, x2, xy. Right? And this is a sort of delicate point, not obvious point. I have to make a choice at that point. And the choice I make, it seems to be completely harmless and completely trivial, but actually it's rather important. So the thing I'm going to do here is I'm going to take my F13 of T1, T2, and I'm going to say, so this is a sum of terms, t to the I, t1 to the I, t2 to the 13 minus I. Right? And I'm going to say in every term here, either I is greater than 3, or 13 minus I is greater than 8. Okay, so I'm not necessarily doing, these are not necessarily the best numbers I can write here, but you have to agree that what I say is true. So if I is greater than or equal to 3, then I've won. If I is less than or equal to 3, then this number here is greater than something, is certainly greater than 8. Yes, and so I can write this F13 as being something fixed of degree 10 times T1 cubed, and then I choose to write this b of times T2 to the 8th. Yes? So this is just, I'm just playing with a homogeneous polynomial in T1, T2 of degree 13. I'm saying if I take out all the stuff out of these terms here, right, the thing I'm left with is a polynomial of degree 10, and so it can be written in x and y, in the xi and y. Right, and then something, so this is of degree 10, and this one's of degree 5. So I'm going to write this A10 of T1, T2 equals A2 of x1, x3y. Yeah, so I'm just making some arbitrary choice of this.
Sorry, why can't A have z's in it?
I'm sorry?
Why cannot A not have z's in it?
It can't, because I say so. Look, we've got a hyperelliptic curve. Hyperelliptic curve is a double cover of the plane. It's a Galois plus or minus 1. All the linear systems on it have a basis consisting of elements in the plus eigenspace and elements in the minus eigenspace. So the z here, so the v is anti-invariant. V squared is invariant. The v squared is a polynomial T1, T2 only. Yeah? And the z1 was t times v. So I'm, yeah, okay, I mean, so look, I have, these are 6 equations. 6 equations in this determinantal form. And I'm getting 3 new equations. I'm sorry, I want to clean some board and I don't want to go too far away from here, so let me clean this. So I'm going to write down two choices of rendition. Right, so on the one hand I'm going to write A x1 minus b x3 to the 4th. So I'm going to write down z1 squared equals z1, z2 equals a x2 minus b x3 squared y, and z2 squared is a x3 minus b y squared. Okay, so you see there's this little kind of dance going on here where I'm writing down 3 equations. It's really only one equation, but just sort of moved through a linear system. So every term here, every term in the succeeding equations is obtained by taking something from there and replacing it by something from there. Yeah? And so here I'm replacing x1 goes to x2, x2 goes to x3, and here I'm doing x3 squared goes to y, and x3 squared goes to y again. Yes? So this choice is called A. Right? And then there's another choice where I'm going to write another choice called B. And here I write alpha x1 squared, alpha times x1, x2, and alpha x2 squared minus b x3 the 4th minus b x3 squared y. minus b y squared. Okay. So I've taken the A here and I've written him as, this is A2, and the B I'm writing as B1. So the A2 are just something which is quadratic in x1 squared x1 something quadratic in x1 x2 x3 y, and this is something which is linear. The B is something which is linear in x1 x2 x3. Right? And here I'm just saying, well, I've got this AX. When I see AX, I'm writing I'm writing alpha. I'm writing A equals alpha x1. Right? And then when I do alpha x1 squared, alpha x2 squared, that's just exactly the same thing. Right? And here I've got alpha x1 x3, and here I'm making a choice. So there's a difference here. Right? So this looks absolutely trivial. It looks that I'm just sort of saying, well, these are two different ways of writing the same element in the ring. So in the ring, x1, x3 is x2 squared. So here I've chosen to keep the x1, x2, x3 here. And here I'm choosing to just think of these as quadratic, x1 squared, x1, x2, x2 squared times some fixed coefficients. Right? So, you know, it looks as if I'm making some completely stupid distinction between these two different forms. Right? However, the point is that I start off with this matrix, and because this is a plane conic and so on, I'm writing this equation x1, x3 minus x2 squared. Right? So this matrix has this tiny little bit of symmetry at the front of it. That looks like a symmetric matrix. When I write this thing here, x1 goes to x2 and x2 goes to x3. That's x1 goes to x2. Hey, coincidence, this x2 is the same as x2, so I can do x2 goes to x3. So when I write A there, it depends on keeping this x2 equals x2. Whereas here, this is just quadratic in the rows of the matrix, and I could let x1 goes to some other x1. Right? So if you write these equations in formats involving A, then it turns out that you can lose the base point. Whereas if you do it in format B, it turns out you can allow the quadratic form. So A allows the base point of P plus 2G12 to go away in deformation. Families. Whereas B allows a quadratic equation x1, x3 equals x2 squared of rank 3 to become x1, x3 equals x2, x2 primed of rank 4. Right. So this is the place where the two irreducible components of Horikawa's moduli space are changed, are separated. Okay. So you know, you can see these equations in my papers. So these 9 equations. So the 9 equations. Wedge 2 of that 2 by 4 matrix equals 0, and Z1 squared, Z1, Z2, Z2 squared. 9 equations. Right, they can be written as unprojections. Okay, so that's the advantage of this, of all of this kind of language. It's the advantage of taking these polynomials in T1 and T2 and treating them as tokens, right? So if you think about this set of 9 equations, these guys and the equations A, the thing you notice is that there is so if I take the 9 equations with the choice A, then x1 appears linearly in 4 equations. Right? So the x1 here, if you think about how x1 appears in these determinantal equations, it's multiplying x2, it's multiplying y, it's multiplying z2, and it also appears here once as a linear term in one of these equations, right, and not in the others. Right, and so this this means we can, if I write down the equations without the x1, this is a 5 by 5 Pfaffian. Right, and I mean, you can just check that the thing it's a Pfaffian of is this 0, x2, x3 squared, z1, x3, y2, z2, z2 minus by2, and minus a. Right. So I told you which of the 4 equations involve x1. If you think about all the other equations, then, for example, there's x2y equals x3 cubed, and that's here, x2y equals x3 cubed. Right. So later on, this y will be y2. Yeah, and so, you know, for example, this equation, z1, z2 is ax2. z1, z2 here is equal to ax2 plus x3 squared. So, you know, you just have to, this is the Pfaffians of, the 5 Pfaffians of this guy. Right, and so the x is multiplying x1. The variable I'm projecting here is multiplying x3, y2, z2, and a. Right, and so therefore this is a Tom1 unprojection. This is a Tom1 matrix. So, you know, this is a sort of complicated ring involving 9 equations and 16 syzygies, but I'm telling you that there's sort of this basically easy and basically mechanical way of treating it. And so I'm, you know, having done this, all of these codimension foreground sign calculations that you've heard me lecture about in the last few weeks, I'm quite good at it. And so it turns out that the unprojected equations, so in other words, I put x1 back, are the 4 by 4 Pfaffians of a 6 by 6 extra symmetric matrix. Right. And so I write the same thing, 0x2 squared x3 z1, sorry, x3 y2 z2 z2 minus by2 and minus a. Sorry, I haven't finished. In fact, I've done it completely wrong. I'm sorry, this is just to make it more beautiful. I write it in this order. 0x3 squared y2, z1, z2, z2, z3. I'm sorry. Okay, so if I strike out this row, then what I get is just this matrix with two of the columns interchanged. Yes? So the thing I'm writing down here is an extra symmetric matrix. It's a 6 by 6 skew symmetric matrix written in a block form like this, where this guy here is symmetric, and this guy here just repeats this one. The 3 by 3 block here repeats this block here, except there's this little factor here, B3. Yeah? So the point is, I can now just take these equations and put lambda there. Yeah? So I'm not really explaining this extra symmetric matrix, but you know, and you can easily compute all the Pfaffians here. You will discover that there are, instead of having 15 independent Pfaffians, I have 9 Pfaffians and 6 repeats. So because of the symmetry of the matrix, because of this extra symmetry, there's, and this defines a 9 by 16 format, where all the syzygies are contained implicitly in the format. Yeah. So when the lambda was 0 there, I'm just repeating the equations that I have over there. Yes. Now, but I say if I put lambda in there, I get I get a deformation of the set of 9 equations to a new set of 9 equations, and the 16 syzygies also deform away. So this is a flat deformation. You know, I mean, I'm telling you a computational device that allows you to bypass all of this deformation theory. Yeah, and so you know what's really happening here. So when the lambda is 0, these are just the equations of the original variety. When the lambda is not 0, then I have equations here. Lambda times z1 equals something, lambda times z2 equals something, and lambda squared times this b, which may incorporate the y2 in it. So when lambda is not equal to 0, lambda z1, lambda z2, lambda squared times b eliminate z1, z2, and y. Yeah, and so you know, you notice here that I absolutely need this symmetry x2 goes to x2. Yeah. So if I make the other choice here, then I have these matrix. I have when I haven't changed any of the alphas or anything, then I have exactly the same set of equations. I have exactly the same set of 9 equations with 16 syzygies. However, the 16 syzygies, now these equations here are just simply quadratic in the rows of this matrix. Right? This is a quadratic form in the matrix, in the rows of the matrix, evaluated on the first line squared, the first line times the second line, and the second line squared. Right? And so in family B allows me to go out to x2 not equal to x2 primed. So I can make a variation here where these x2 are allowed to change. And that means that the image, so, Horikawa's picture is, here is x goes to x5, goes to P3, P5, P3. And there's family 1, which is that x is equal to x5. There's family 2, where x maps 2 to 1 to a quadric, and the quadric is of rank 3 or of rank 4. Right? And these are called 2b and 2a. Right? So these are covered by format B. Right? So if I choose to write the equations here in this form, so that they're just quadratic in the rows, then I have a divisor in a scroll, and I can change the scroll a little bit. I can vary the scroll a little bit whilst keeping the divisor in the scroll, and I can achieve this guy. Right? Whereas if if I choose the format A, then I can take lambda not 0. Right? And that means that gives me these two families. So the family 1 and the family 2b are both contained in the same set of equations here. Right? So this is perhaps a little bit rough, but so Horikawa's picture is of the moduli space is like this, where there's family 1 here, family 2a here, and then family 2b there. And then each of these two big families is 40-dimensional, full moduli, whereas and is unobstructed. Whereas if this line along the middle there is 39-dimensional, and the obstruction is x2 prime minus x2 times lambda equals 0. So my little graded ring games tell you how to make all the surfaces in this leaf and all the surfaces in that leaf. They don't actually tell you this. They suggest it, but they don't tell you it. That if you want to see that, you have to do the infinitesimal deformation. Okay? So, this is, in some ways this is quite unexpected. So we get this, Gorenstein and projection trick, the thing I've been doing here. Take one of the variables, treat him separately, treat him as an unprojection variable. So then I go down to these matrices, which very often turn out to be in these standard Tom or Jerry formats. Right? So I get a matrix in this format, and I say, aha, the important thing about this matrix is that it's a Tom. Right? These 6 entries here, instead of being 6 general entries, have 2 coincidences among them, saying that these 6 elements are actually just 4 elements that are contained in a codimension 4 complete intersection ideal. Right? And so if armed with that knowledge, knowing that this is a Tom matrix, I can vary everything else here. I can make this one into a Y1, for example. I can make this one into a lambda not 0. And, so I get, for free, flat deformations. Okay, so I want to talk a little bit about about Dix's thesis, which, as I say, is going to take me into very amusing and not finished territory. Yes.
Just that you don't check the dimensions in your calculation.
I'm not doing the calculations very thoroughly, as you can see. If I do this, I'm getting a key variety. So replace everything here. Replace the x3 squared by y1. Replace everything here by independent variables as long as the symmetry is maintained. Right. Yes? Then I get a single key variety. And all of the Horikawa quintics, all of these surfaces here are obtained by, all of the surfaces in that leaf, the 1 and the 2b surfaces, are obtained by pulling back from this, by doing a regular pullback from this construction.
In principle, you could calculate all the parameters in your regular pullback and in your format and see, count the number 40.
Yes.
But you still wouldn't know that that was the answer because you still would have to do...
Look, as you may have heard over the weekend, Fabrizio complains that I never bother to do the dimension calculation to check that I've got complete formulas. Right? The thing that my methods will prove that every surface is given by this construction. Right? You know, I'm sorry, I'm not giving a proper answer to that, and it's partly just because I really don't want to get into deformation theory. It's really unpleasant, and
The short answer is yes, every surface is in this format.
every surface is in this format, yes. So, you know, Horikawa also did deformation theory. And, you know, what Horikawa did is always completely correct. I mean, there's no, but he's sort of basing himself on analysis rather than on algebra. So let me do this. So this is Dix and Horikawa. I mean, Horikawa was first, of course. But so the thing here, I'm starting from a curve C, and the curve C is going to be hyperelliptic of genus something or other 5. And now it's got a linear system which is like this: P0 plus P infinity plus, and then P1 up to however many it's got to be. Yes? So it's a sort of similar picture. Here's P1. Here is my hyperelliptic curve. I'm marking 2 of the Weierstrass points like this. Right, and then there are some other number of Weierstrass points. I'm again, these are points, this is a divisor on C. Right, and the linear system, so I want to talk about surfaces of PG equals 3 now, k squared equals 4. So, as I said, if I look at phi k, multiples of phi k, so the pluricanonical ring, the thing I'm expecting is that x maps to x is x44 in P of 1, 1, 1, 2, 2. That's a surface of general type, and so, you know, here PG equals 3, that's the map to this P2, x1, x2, x3, and I'm expecting to see a 4-to-1 covering. Right? And so there's another possibility. There's a possibility that x has 1 base point and maps to a codimension 3 variety in P of 1, 1, 1, 2, 2, 3, which we'll see later. But so, you know, there the curves are sort of naturally trigonal. Here I'm going to assume there are 2 base points. And I'm mapping to codimension 4 in P. So again, 1, 1, 1, 1, 1, 1, 2, 2, sorry, 2, 3, 3. Yeah, and so you know, I'm not going through the Horikowa analysis, but it's not very difficult. I've got a linear system on a surface. If I take account of the base points, and then either there could be one base point, and I've got a map which is 3 to 1 to the plane, and then I need some extra stuff in the canonical ring, or I've got 2 base points. So these are the only possibilities. Well, you know, I mean, there's two. We could have a base minus 2 curve, a base minus 2 cycle. That happens, and I'm just going to ignore it. So I want to just forget about the kind of singularity theory aspects of this and think about the graded ring aspects of it. Right, so the curve C has Kc restricted to C, Kx restricted to C, now is P0 plus P infinity plus G12. Right, so it's this picture. And so again, I really want to think of I want to think of U from OC into OC of this P0 plus P infinity. Right, and then I want to think of V as being OC goes into OC of P1 plus P10. And then and then there's T1, T2. This is just the G12. But I can arrange this that U squared is T1, T2. So, you know, it'd be sort of more natural to think of this as T0, T infinity, but yes. So there are 2 points. If I've got 2 points on P1, I can normalize them to be 0 and infinity, and those are the points, the T1 and T2 points. Right? And so I have U squared is T1, T2, and I have V squared is F10 of T1, T2. And I'm going to play some games with the F10, just like the games I played over there. Okay, so, you know, this is the bigger ring. This is the everything in the ring of Kc on C, Kx on C, is expressible in terms of these elements in a bigger ring. On the other hand, I'm not really allowed to write these down if I'm only working in the ring itself. Okay, so we're going to get codimension 4 Gorenstein rings, and they have different deformations that allow the base points, the 2 base points of the linear system, to move away. Right, so first of all, let me write down the ring. So the ring is so the linear system is the 2 fixed points plus the G12, and the 2 fixed points are U. So I write down U T1, U T2 in degree 1. Right, and I call these x1 and x2. And then in degree 2, I have y1 is t1 to the 4th, and then there's x1 squared, x1, x2, x2 squared, and then there's y2, which is t2 to the 5th, 2 to the 4th. Yeah. So when I write monomials like x1 squared, then x1 squared, x is ut1, so there's a u squared in there, which is t1, t2. So these 3 guys in the middle are the ones that are divisible by t1, t2. So they're the elements of the canonical system of C that vanish at P0 and P infinity, respectively. Yes? And then degree 3, so you know, these kind of rings are always generated in degrees 1, 2, and 3. So VT1 Z2 equals VT2. Yeah, so the same kind of reasons. This is the 10 Weierstrass points. So if I take 10 Weierstrass points except for those last two. So if I multiply either by T1 or T2, I get elements of the linear system 3 times this divisor. You know? And so the relations, you can see the relations. So wedge 2 of y1 x1 squared, x1 x2, x2 squared y2, z1 z2. Right, I'm just writing down that the ratio between, whenever I write these lists of monomials, the ratio from one monomial to the next is the ratio T1 to T2. It's a fixed ratio. Right, and then there's this game, which I have to play, you know, even more slightly. Okay, so the reason for making a fuss about this, I mean, I made a lot of fuss about it there, maybe more fuss than clarity. So if I take the kind of relations that are holding here between these elements, if we're in the bigger ring, they're just identities. So, you know, T2 times this and T1 times this are just the same element as long as we're in this bigger ring with these elements. So if I go to the ring with these generators and some relations, then these are now non-trivial relations between the ring. And when I deform away, they're not even that. They're relations modulo all the deformation parameters. So that's why you have to be careful here. Right? So exactly what I'm going to write here depends on what it is I'm trying to do. Right? And so we'll see that there's lots and lots of things, there are several different things I can do, and that they give me different possibilities of deforming. So first, so there's a little section here which is deform away the base point P0. Right? So the thing I've got is P0 plus G12 plus P infinity, and I want to take this to get the curve together with this, it's a hyperelliptic curve together with this linear system, and I want to deform him a little bit to get C, you know, deformed curve C, and then a linear system here which is a G13, but leaving the fixed point P infinity. Yeah, so I'm deforming away one of the base points without deforming away the other. So for this, I'm going to write down wedge 2 of a matrix that deforms that matrix, and I'm going to write down y1 c x1 x1 x2 d y2 z1 z2 equals 0 and z1 squared a y1 plus b d squared. Yes? So the thing I'm doing here is, this was x1 squared, there. I say, I don't really care that it's x1 squared, but I do care that it's got an x1 in it, right? I must have an x1 in it in order to be able to continue, right? So I write this as x1 times some token. So the x1 is a new variable if you want, and in the particular case, I can substitute x1 equals c. Right? And then this x2 squared, I say I don't care what he is, I'm just going to call him d. Yeah? And now I take these equations and I say this f10, well, every term in f10 is either divisible by t1 to the 4th or t2 to the 6th. Every term in f10 is divisible by is one of those, and then I sort of do some similar things here. So the stuff which has got lots of t in it, I can think of that as a multiple of y1, and then I can replace y1 by x1, y1 by cx1 here, and then x1 by x2 here. Right, so these are still rolling factors. Right, I'm going from there to there and from there to there by each time replacing something in the top row of the matrix by something in the bottom row of the matrix. So that guarantees that, you know, this is a divisor on the scroll, or it's a way of writing down the equations so that the syzygies are already contained in the way I've written down the equations. Yes? So, I mean, you know, there's some little calculation to do to make sense of this. So, I say y1 is an unprojection variable. So remember my trick. I say, let's consider the guy y1, right? And so y1 is there in the matrix. He multiplies these three, right? And he also multiplies a. So y1 is, in the equations, is multiplying x2, y2, z2, and a. Right? And otherwise, she's not appearing in the equations at all. Right? So this means that I'm just taking the equations and I'm, you know, putting them in alphabetical order or something in the way I like to do it. And I say y1 here appears linearly in 4 of the equations and not at all in the other 5 equations. And so the other 5 equations will be a Pfaffian matrix, right? And so you look at the equations and you say, aha, you know, if you really enjoy doing something once, then you should try to do it again. Maybe not to excess, but right. And so, you know, here's x2. So who does x2 multiply? x2 multiplies x1 and d and z and AC, right? And otherwise she doesn't appear in the equations at all, right? So x2 is unprojection variable. With, I'm over time, aren't I? X2 times, and then there's y1, d, z1, a. So these are both Tom matrices. I can write out the 9 equations in a form suitable to deform. Okay, so I'm sorry about organising the lecture so that I stop at an interesting point, but let me explain this at the end. So what I'm going to say is, you know, I've got some little algebraic tricks here, which are just basically just elementary tricks that you've heard me talk about before in this context of Tom and Jerry, right? And they say, given this set of 9 equations, well, 9 equations for 16 sisters is a complicated thing. However, there is a nice way of thinking about it as one of the variables separated out, thinking of this as 4 linear equations and the 5 by 5 Pfaffian. Right? Here I can do it in 2 different ways, and that is going to give me all 9 equations in a very nice form. And then I can take the things appearing in the matrix and I can vary them. I'm going to lose this format. This format won't be here. When the curve stops being hyperelliptic, of course I don't have this form of the equations anymore. So eventually I have to throw away these equations, but before throwing them away I can do this trick with them. Right? So I can get rid of the base point P naught, and then I can turn around and say, well, now let's get a P infinity in a similar way. And there are subtleties here. But anyway, let me leave that for the second half.